Today we will discuss some special cases of the MeshCurrent method. Recall that the MeshCurrent method was a systematic application of Kirchhoff's voltage law. So today we will examine what happens when you have a current source in the circuit. But before we get started on the special cases, let's do a mini review of the MeshCurrent method with a problem that I've taken from the FE preview book. So let's assume that you've labeled your current and you have a clockwise current IB and a counterclockwise current IA. Let's look at how you actually solve this problem. So the first thing you would do is write the KVL equation for mesh A. Since the IA and IB both point the same direction through the 8 ohm resistor, this is actually going to be 8 times IA plus IB plus 12 IA and that equals 20. The KVL equation for mesh B is going to be 8 times IA plus IB again, minus 40, and that equals 0. So we end up with 2 equations and 2 unknowns. So IA is equal to negative 5 over 3 amps, and IB is equal to 20 over 3 amps, which is approximately 6.7 amps. So the answer is letter C. So now let's discuss how you handle current sources when you do the MeshCurrent method. There are 2 types of current sources. One of them is when you have a current source in an outer branch, such as in this bottom left circuit. The 5 amp current source is in an outer branch. Since we use the MeshCurrent method to find unknown mesh currents, for the 5 amp source, what you would put is I2 is equal to negative 5 amps, and you do not do KVL. Recall, KVL is used to find mesh currents. So if I know that that current is negative 5 amps with respect to I2, you don't do KVL. It's also important to note that I made I2 equal negative 5 amps because the 5 amp current source points counterclockwise while I2 points clockwise. If I2 had also been labeled counterclockwise, then I2 would equal 5 amps. The second type of current source we could have in a circuit is when the current source is shared between meshes. When the current source is shared between meshes, it's called a supermesh. The current source and anything in series with it becomes part of that supermesh. And just like with supernodes, we perform KVL and KCL at the supermesh. However, it's a little different for how we do that. So no KVL. But over here, the KVL equation for the supermesh is actually going to be the sum of the voltages negative 20 plus 6I1 plus 10I2 plus 4I2 equals 0. And the KCL equation for the supermesh is the relationship between I1 and I2. Since I2 enters the bottom node and I1 leaves the bottom node and the 6 amp leaves the bottom node, the KCL equation is I2 is equal to I1 plus 6. Students sometimes ask me if it's better to do the node voltage method or the MeshCurrent method on a certain circuit. And I'll tell them, it really doesn't matter. You'll actually get the same answer whether you do node voltage or MeshCurrent as long as you don't make a mistake. However, sometimes one method is more efficient than another one. For example, if I have mostly series connected elements similar to a loop, then I would probably do KVL or mesh analysis or the MeshCurrent method. Or if I have mostly parallel connected elements, current sources, something like a single node pair, I would probably do nodal analysis or the node voltage method. If I have a circuit with fewer nodes than meshes, it's probably better to do the node voltage method. Fewer meshes than nodes, it's probably better to do the MeshCurrent method. because typically what you want to do is to select the method that reduces the number of equations. The less equations, the less points where you could potentially make a mistake with your math or with writing the equations. Also, you want to sometimes consider the information required. If I ask you to find node voltages, it's probably better to do nodal analysis. If I ask you to find mesh currents, it's probably better to do the mesh current method. Also, if you don't want to deal with supernodes, you may do mesh current, or if you don't want to deal with super meshes, you may do node voltage. So now that I've kind of given you some of the reasons why I choose to do one versus the other, look at the concept question at the bottom of the page and determine whether you think it would be more efficient to do the node voltage or mesh current method and why. Hopefully you've had a chance to look at the circuit and come to your own conclusion, and hopefully you did select the mesh current method. Let's talk about why. First of all, there are only 4 meshes. So that would be 4 equations. However, how many nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 nodes. That doesn't necessarily mean you're going to have 9 equations though, because you do have some voltage sources. However, depending upon where you put the ground, because you could put the ground here, or here, or here, you're going to have 2 or 3 supernodes. And you have voltage sources, so that would give you at least 1, 2, 3, maybe 2 or 3 voltage values where you won't have to do KCL, but yet and still, you're probably going to still have at least 6 or 7 KCL equations versus the 4 KVL equations for the mesh current method. So really, no matter which way you look at it, the mesh current method is definitely the way to go. Okay, let's try an example with a supermesh. Recall, a current source that's shared between branches and anything in series with it creates a supermesh. So for the circuit that we have here, the 5 amp current source is the supermesh. And remember, whenever we have a supermesh, we do KCL and KVL at the supermesh. So I'm going to label this first current clockwise I1 and the second mesh current clockwise I2. So KCL is a supermesh. Since I2 comes into this node and I1 leaves the bottom node, the KCL equation is I2 is equal to I1 plus 5. The KVL equation is the sum of the voltages around the larger loop taking the current source out. You're not really taking the current source out, but that's a good way to think about it. You're summing all the voltages, but you're skipping over the current source. So that equation yields negative 100 plus 3I1 plus 2I2 plus 50 plus 4I2 plus 6I1, and that equals 0. So if we collect like terms, we're going to have 9I1 plus 6I2, and that equals 50. Solving this system of equations yields I1 is equal to 4 over 3 amps, and I2 is equal to 19 over 3 amps. So now let's show that this circuit obeys the law of conservation of energy. The first thing we'll do is we'll label the voltages for the voltage sources and the currents for the current source on the table. So the 1.33 amps is the current for the 6 ohm, the 3 ohm, and the 6 ohm resistors. So let's put that on the table. The 100-volt source delivers power, and it delivers 133 watts. The current for the 50-volt source is 6.33 amps, and the power is 50 times 6.33, which is 316.5 watts. Since the current goes into the positive and out of the negative, it delivers power. We'll come back and do the voltage for the 5 amp current source at the end. So now let's do the 2 ohm resistor. The current for the 2 ohm resistor is 6.33 amps. So the voltage is 12.66 volts. And the power absorbed is 80.14 watts. Now the 3 ohm resistor. The current for the 3 ohm resistor is 1.33 amps. The voltage is 4 volts. And the power is 5.32 watts absorbed. The 4 ohm resistor, the current is 6.33 amps. And the voltage is 25.32 volts. So the power for the 4 ohm resistor is 160.28 watts. And finally, the 6 ohm resistor, the current is 1.33 amps. So the voltage is 7.98 volts, and the power is 10.61 watts absorbed. Now let's go back and do the 5 amp current source. The voltage across the 5 amp current source can be found by using KVL, where we sum the voltage across the 2 ohm resistor plus the voltage across the 50-volt source plus the voltage across the 4 ohm resistor. So the voltage across the 2 ohm resistor is 12.66. The voltage across the 50-volt source is obviously 50 volts. And the voltage across the 4 ohm resistor is 25.32 volts. So when you sum those up, the voltage across the 5 amp current source is 88 volts. 88 times 5 is 440 watts, and that's also going to be delivered. So the power delivered to the circuit is 573 watts. The power absorbed is also 573 watts. So this circuit does obey the law of conservation of energy. Okay, let's start the final example of today's lecture. We have a circuit here. We do have a supermesh. The 5 milliamp current source is a supermesh. And let's label all of the other mesh currents as well. First, we have a 20 milliamp current source in an outer branch. So the name of that mesh is just going to be 20 milliamps. Then we have a 10 milliamp current source over here in this outer branch. So the name of that mesh current is going to be 10 milliamps counterclockwise. This top mesh, we're going to label the current I1. This small mesh here, we'll label the current I2. And the one in the middle at the bottom is going to be I3. Recall we have a KCL equation for the supermesh, so we'll do that one first. The KCL equation for the supermesh is going to be I1 is equal to I2 plus 5 milliamps. So you can get that equation by doing KCL at this node here. KVL at the supermesh will be that entire top mesh if you skip over the current source. So starting with the 4K resistor on the left, you're going to have 4K times I1 minus I3 plus 1K I3 plus 4K times I2 plus 10 milli. And that equals 0. And now since we have another mesh in the circuit, we also need to do KVL at mesh 3. Starting with the 2K resistor, that's going to be 2K times I3 minus 20 milli plus 4K times I3 minus I1 plus 2K times I3 plus 10 milli, because they're flowing the same direction, and set that equal to 0. So when we solve this system of equations, we get the following values. I1 is equal to negative 1.43 milliamps. I2 is equal to negative 6.43 milliamps. And I3 is equal to 1.79 milliamps. Finally, let's find the power associated with the 5 milliamp current source. In order to answer this question, the first thing we have to do is to find the voltage across the 5 milliamp current source. Since the 5 milliamp current source is in parallel with the 4 kilo ohm resistor, they are going to have the same voltage. So that's going to be 4K times 10 milli minus 6.43 milli. The reason it's minus is because they point in different directions. So that voltage is 14.28 volts. And that is going to be positive on the right and negative on the left. So the power for the 5 milliamp current source is going to be 5 milliamps times 14.28 volts, which equals 71.4 milliwatts. Since the current flows from the positive to the negative, that's going to be absorbed. This concludes lecture 4-1 on special cases of the mesh current method.